Right, question 5. We've got a bunch of students, 20 students from a sample. We've got a sample mean and a standard deviation. Well, of what? We care about the ages. So the mean age, that's what we in particular care about. We know that the student ages are normally distributed. So that's given to us in the question. Now, they gave us some sample parameters. No population parameters are known. And they want us to calculate a 90% confidence interval. Well, let's do a quick recap. What's the confidence interval? Well, we have a L and a nu, a lower limit and an upper limit. That's what it stands for. And we are, let's write this first, 90% confidence interval. We are 90%, we can say with 90% confidence that mu is gonna be in between this upper and lower limit, right? So if we keep constructing confidence interval, then 90% of the cases mu is gonna be in between the lower limit and upper limit of this confidence interval. Now what we're asked to do is finding this lower and upper limit, because that's what defines our confidence interval, right? So let's do that. We've got a sample mean of 48.5. We've got a standard deviation of 14.4 years. Let's not forget that. All right. Well, that's actually all we have to do. I mean, for now, it's just filling in a formula that's over here. X bar plus minus t-score that belongs to alpha divided by 2 times s over square root of n. Well, we can do that. It's just filling in some formula, right? Let's do that. Let's do it over here. Yeah. Well, what was x bar? We had an x bar of, let me check, 48.5. And then plus minus t. What's alpha? Have we noted down alpha? Well, if it's a 90% confidence interval, then alpha has to be 1 minus 0.9 is 0.10 is alpha. And we want to do alpha over 2. So alpha over 2 is going to be 5%, right? Times the standard deviation over the square root of 20. What was the standard deviation? 40.4 years. This is going to be 48.5 plus minus. This we have to look up in a table. The t alpha over 2. So we got a sample size of 20, right? That means 90 degrees of freedom. So we're looking in that row. Then alpha was 10%, but we need alpha over 2. It's this column, 5%. So we're gonna be somewhere, let's see, this is gonna be your t-score, 1.729. So let's fill it in. Times 14.4 over the square root of 20. So that's the formula for our confidence interval. Plus minus, don't forget the plus minus, of course. Well, let's move it just here. All right, so this follows that 48.5 plus 1.729 times 40.4 over square root of 20. This is gonna be 53 let's check, 9. Yes, and then 48.5 minus 1.729 times 14.4 over square root of 20. Well, this is going to be 42 plus 4.4, excuse me. Right, so we got our lower limit and we got our upper limit. What follows from this? Well, that we're 90% confident that mu is gonna, let's do it here, mu is gonna be smaller than the upper limit and larger than the lower limit. So what's our 90% confidence interval? It's gonna be L U is well, that's it. That's it for the confidence interval. So we've constructed a 90% confidence interval. Not that hard, just need to know what you're doing. Let's proceed. Let's go to B. Read the question. So suppose we increase the sample size. What would happen to the length of your confidence interval? They ask you whether it decreases or increases. Well, there was this formula. Let's take it over. Right? This was the formula for your confidence interval boundaries. So where's n? We've got n over here in the denominator. So if we rewrite the formula, we get right? Let's make this a bit more. Yeah, that's better. So what happens when we increase n, when we increase the sample size? Right, you remember, suppose, let's not use that. Suppose n becomes real big, then x bar plus minus t alpha over 2 times the standard deviation over something bigger than n. Suppose n was 20 in our case. So suppose now it's going to be 50. Right, then this expression, this is going to be smaller than over 20. That's not really readable. That's better. So what happens when we increase the sample size? We're getting boundaries closer to each other. That means that suppose we had that's the lower limit, and we had here our upper limit. That's in the case n is 20, and now the case n is 50. We suddenly have here our lower and upper limits. Right, this is the distance. And what do we see? We see the distance decreases. So the length of our interval decreases as n increases. And that makes sense, right? So we were 90% confident that mu is in between u and L. So suppose I increase my sample size, I get more information. So I've got more information than I used to have. So I can say with more confidence, I'm more confident to say that my mu is in between some interval, is an element of some interval, right? Since I've got a larger sample, I've got more information. So I'm more confident with stating that mu is in between L and U. That's the reasoning behind it for part B. So it's decreasing as n increases. That's it.